the damping element is very straightforward, and so here I'm going to work on the slide. And actually here for ME408, again, we only consider is a linear damping. And the damping, basically, the majority of the linear damping is caused by, we call it viscous damping. Okay, viscous damping. And let me show, this is a very, I think from your fluid mechanics, from the first or second chapters, you've been sitting with this. That is called the Shin stress in the fluid, right? So everything is linear. The bottom one is fixed. The top one is a plate in between that filled up certain viscous fluid. And the setting is such that the dragging the plate on the top, and when reaching the steady state, the distribution of the velocity within the fluid basically is in linear fashion. Zero at the bottom where the substrate is motionless. And maximum is there, everything is linear. How come they form a linear distribution of the fluid velocity? Because of the viscosity. Because of viscosity. If you remember that equation, that one describing by this. Viscosity of the fluid equal to the Shin stress equal to mu times the velocity square. If you remember that one, and actually is dy dx, dy dx. Do you remember this term? Hope so. Okay. So with those things in mind, and then we can calculate is this. This is the local distribution of the Shin stress. If we consider is the whole plate, then the whole plate has the area. So we simply multiply the Shin stress to the whole area, give us the Shin force. Okay, so that means we do the integration on the both sides and then do something there. Eventually, we will be able to find the force. This left-hand side represent is a force, and this one is dx. Okay, and the right-hand side basically will lead into a very simple description of the term c times v. What is v? V is the velocity here. Okay, and that is a very simple description, and that is a term we're going to pick it up in vibrations. Actually, we are not going to using this equation, we're going to use the template. So basically, this is a term, if you like, you simply write it out. The force equal to CV. C is called the damping constant. Okay, that is, this equation is what we're going to adopt in vibrations. And in between how we get this one back to your fluid mechanics, let me skip a few steps here. So in particular, if you're really concerned what is the damping constant, C is related to area. Area is the area of the fluid contact, and mu is the viscosity. In particular, we call it dynamic viscosity. D is the distance between the stationary and then the surface of the fluid. And so, for example, if, say, in cars, in the suspension of the car, they have the kind of the suspension. I don't know what's called. It's not CE. For car, you know the suspension system. Shocks, whatever. So basically, they are using the cylinder, and within the cylinder, they filled up with the fluid, oil. Okay, so let me draw that one. So using the 3D, so that is the cylinders here, and they have certain piston or some kind of rod here. Okay, so that is this thing, and in between, they filled up with oil, Okay, so basically in between is the oil, and in certain configurations, say this one piston is attached to the frame of the car. Okay, and on the other side, this attached to the wheel of the car. Okay, so to reduce the damping, basically their planning is to pick up the displacement of the wheel transmitting, and hopefully that transmission of the displacement from the wheel to the drivers, to the passenger, they can feel a bit less, right? Okay, so basically that one, basically taking up is in relative motion. So assuming the car has the displacement, then we call the YT, and this one, from the ground, we call the X of T. So they simply take it up is a relative displacement. Actually, the taking up is a relative velocity. That is a relative velocity. That is a term here. And C is determined by this term, A mu D. What is A? A is a contact area. So basically, that is a contact area. You can assume that is the circumferential areas of the piston, for example, or you can approximate the circumferential area of the piston there. Okay, and mu is the velocity, the viscosity of the oil. And what's the D? D basically is the distance here. For any the kind of suspension, you can do the very rough estimation to determine the damping constant there. Okay, so that's one example. Okay, so with this one, keep in mind, and again, what we're going to use in vibration is F equal to CV. With this term in mind, then we can introduce the dampers in similar serial or in parallel connections. And C, again, we call the damping constant. And that formula is the same as in the spring, because, again, what is the force? The force due to damping equal to C times velocity. Okay, so let me pick X as a degree of freedom. Compared to the damping, and compared to the spring, our force equal to this term. Okay, so if you take a free body diagram of the dampers, then basically they have the same reasoning. So the formula is the same. Okay, so let me skip the details. We simply pick up for parallel, then we have the same thing here. Okay. So the same exercise applied from the spring to dampers. How to determine whether a connection is in serial or in parallel connections. Again, using our tube. If that connection is in parallel connections, then that means for both components, they have the same displacement, right? So that is the tip I share with you in the spring. Again, for a connections, if that is in serial connections, then the force in each component must be the same. We're simply using the two tips to tell when the configuration will be more complicated. We stick with the two conditions to justify whether that connection is parallel or in serial. Okay. We can begin to work with a few more examples here, and for this one. So that's what probably we can have a new